Okay, so I'll be starting now. I'll first share my screen. Yeah, is the screen visible?
Yes, sir.
Cool. So let's proceed. Yeah, so as always, introductions. So this this NPTEL course is analog IC design, and it's taken by instructor Dr. Shankaran Aniruddhan. He's from IIT Madras. So he's from IIT Madras. Myself, my name is Mayank Anupam. I am the tutor for this course. So I'm also a PMRF scholar. I'm a PhD student at IIT Kanpur. Fine. So uh, before starting this week's content, so I want to ask you. So was there any trouble in this assignment?
Sir, this one is fine, sir. Sir, I had trouble in week 4, sir. I'm appearing for final exam also.
Okay, so you
Is
have
going
trouble
to
in
happen.
week four.
Yeah, week 4. I
Okay,
know
about
week
that.
4, week 4, I think, sir.
Week four. Okay, that is
Week
far
4.
back. Let's see.
Yes.
Week four.
I don't know, sir. I need practice, sir. I need to practice. I'm lagging my practice. If I get it. Sir, that's why I'm referring the reserve book, sir. But I'm not. I didn't get any solution manual, sir. If I get a solution manual, it would be a better reference to check where I am correct.
Okay, I
That's,
understand your concern, but I seriously don't have an idea where you can get a solution manual. It's
sir,
maybe you can
at the
search
time,
online. Might be
yeah, while
available.
you're preparing, how in which way you prepared, sir? Means parallelly doing one more course also. Circuit analysis for analog device. Shanti Pons are also
Yeah, 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 yeah. I understand. Yes.
both are related, sir. Somewhat noise calculation.
Correct, correct,
Yeah.
correct.
That's why I will relate everything, sir. That's why can you please suggest me any
Yeah, so
alternate?
that's right. That's what. Now I never referred any solution manual. So whatever doubt I had, I went ahead and asked my instructors, and also I never consulted a solution manual. So I understand your concern. So what you can do is you can search online. If you don't get that, maybe practice the this thing. Maybe you can practice from the solved examples. So there are plenty of solved examples in Razali's book. Okay, so there you can and those solved examples, they are also very good. So if you solve them properly with so that will help you understand the concepts much better, and then you can solve your questions. So I also tried to solve some questions. Um, Basically, I want to cover the samples, okay, in these tutorials. I try to cover the samples so that you are not lacking on anything. So what I can say, so you were not attending the previous this thing tutorials, really.
I attend, sir. I will watch your recording sessions every week, sir.
Okay, fine. So it's fine, but
I came
I
on first week one, sir, but I have a one more live also, sir. I'm parallelly doing three courses, sir.
okay, I
That's why
understand.
I'm not able to
What I'm saying
manage.
is, you see, maybe you see if you watch the videos, it might not help you that much because you see your questions will be your own, right? It might have happened that no one would have asked me that question, and I would have simply not talked about it. So what I would suggest is we have other three after today we have again three this thing sessions, right? What I
Yes,
would
sir.
suggest is that brush up you basically revise everything which you have learned till now, and then solve some examples, and then come to me with your questions, okay? Maybe after that I will be able to help you.
Yes, sir. Why Aniruddhan sir lectures are not adding, sir? I mean, not getting idea.
Yeah, I have no idea. I mean, I was hoping that his lectures would be available after week 6. I was I was hoping that, but yeah, so he has not
Yeah,
uploaded
this
any
week a
lecture.
noise calculation I referred Aniruddhan sir. That same type of problem came in assignment also.
Yeah. I get it. I understand. So basically, that's why na.
Question
Once I
paper
was,
is will be
I didn't know. I
given
don't know
by
why it is not given. Basically, why he has not uploaded any lecture of his own. I don't know. I have no idea.
question paper will be given by Aniruddhan sir or Nagendra Krishna Guru.
Though these logistics I don't know. Okay, I
Uh,
I seriously have no idea about these logistics. My job is extremely exclusive of what is happening in this course.
yeah, sure, sure, sure. Thank you, sir.
Yeah,
Next week I will revise, sir. If I have
definitely,
any queries,
definitely.
definitely.
Yes.
Yeah,
Definitely.
continue, sir. Thank you, sir.
Yeah. So any no doubt in this assignment, right? Anyone? So I will
Yes, sir.
simply
For me, it's okay.
okay. So I will simply go ahead and not discuss this question in that case. Anyway, this question exactly same kind of question I discussed in the last week. This thing also video also. If someone has any doubt, they can refer to that video. Right. So fine. Let me go ahead and discuss this week's questions. So before discussing this, let's move on to other questions. Fine. So in this week, we basically learnt about what? Yeah. So in this week, we learnt about differential circuits, right? Differential amplifiers. So differential pairs basically. So even the questions are also framed for that only. And you also learnt about common mode range, basically how to find the input range and output ranges such that all the transistors remain in saturation. These things we discussed. And yeah, so basically this is a very important part of any design. When you start designing something and you start designing an amplifier, you have to you will be given with some specifications that your amplifier should work with so much of input variation. It should be able to handle this much of input variation, and moreover it should be able to provide this much of output swing. So all those things you will be given, and based on that you will have to start your design. So you have to have a you have to have an idea of how to calculate these things, basically the input common mode range, output common mode range, moreover the input swing, output swing, all those things you should be able to calculate these things. Okay, so start this let's proceed with this question. mm. So yeah, so let's take the first question first. uh, yeah, okay, fine. So in this question we have to find the differential mode and common mode gain. Okay, so this is a very common circuit. Okay, this is a very common circuit. You can recognize the circuit if there was no resistor present, right? You can very easily identify the circuit if these resistors were not present, right? So guys who are present,
Yes, sir.
please
Yeah.
participate. Okay, otherwise I have no idea who is listening, who is not listening. I will simply be talking to myself. That is not a very pleasant experience. Okay, so come on. So due to these resistors something changed, right? So now tell me how will you calculate the gain in this case, the differential mode gain? So basically differential gain is between these two terminals. This is not properly written. Okay, this is V bias. Yeah, so we have this differential mode gain between these two
Sir,
terminals.
gain will be minus GM1 into like arrow 3 parallel
Just give me a second.
uh,
Minus GM. How much? GM?
gm 1
Okay. So
into
consider,
into
assume these two have the same GM, okay? GM.
yes, yes.
Okay. So what after that?
After that, the resistance of RO3.
RO3 you are saying.
Yes, yes. RO3 parallel 1 plus GM RO1 RX.
1 plus GM
RO1 RX.
R1 RX.
And we can and one yes, and RO no, okay, 1 plus GM are not into RX.
Just ignore that, okay? So don't complicate your life so much. GM1 times RO1 GM.
Into RX, yes.
GM times RO times RX, right?
Yes, yes, yes.
So is it true, by the way? Are you sure about it?
Sir, if the inputs are so small, then the RX, the connection between two RX is a ground point, so we can write this.
That's what I'm saying. If this is a ground point, okay. By the way, this
Yes, sir.
was this covered? I mean, was this? Do you know? Do all of you know this concept that if the inputs are anti-symmetric at the input, so you can assume that this is a ground, virtually short for differential mode operation.
Yes, sir.
No, no, not you. I mean, yeah, you understand, but other people, do you know this?
No, sir. I have idea for balanced output and unbalanced output. According to that,
Yeah.
current
So
will
let's
be.
let's let's discuss that. Okay.
Yes, sir.
Fine. So you see, let's talk about. Let's forget the circuit. Okay. Let's talk
Hmm.
about a seesaw. You know what is a seesaw?
See, so uh, shortcut, sir. Could you?
Seesaw. It's a this thing. Seesaw. This is what I mean. You must have seen in your childhood, right? This is like two people are sitting here. It is going
Yeah,
here,
yeah. Balance, sir. Yeah.
right?
Uh,
About a fulcrum. It is moving here, right?
yes, sir. If it
So
is balanced output, then current will be zero, sir.
yeah, one second,
Unbalanced,
one second, one second. Let's
yeah.
let's let's reach there, right?
Yes, sir. Sure,
So
sir.
everyone knows what is a seesaw, right? You have seen that it is basically there is a point where it is balanced, right? There's a point where it is balanced. Now, if two people have like basically if two people sit on it, it will move like this and then come back like this, right? This is how it is done, right?
Yes, sir.
I mean,
If I
this is
went
how
to
it is
weights are
supposed to work,
equal, yes, sir.
right? Now if
Hmm.
now suppose what happens is that now let's say I uh, I put two people here, but both with the same weight. Okay, both have the same weight. Okay, so what should happen?
It would be straight, sir. It won't bend on one
It
direction.
will not move, right? It should not move
Yes, sir.
ideally, right?
Yes, sir. Yes,
Correct.
sir.
So the analogy here is that basically this is like a common mode for this particular system here, right? Both systems are experiencing the same amount of weight. Both sides are experiencing the same amount of weight, right? In the same direction. So there is no torque, right? No effective torque. So it will stay there itself, right?
Exactly, sir.
Right.
Hmm.
Now let's consider the case where one guy is sitting here in this one guy is sitting here having some weight, and I am pushing from this side, okay, in exactly the same amount of force that that he's pulling it down, okay.
Yes, sir.
So now what should happen? This will move up, this will move down, right?
Yes, sir.
So
Hmm.
the analogy with the circuits case is that this is a perfectly this thing anti-symmetric input, okay. To this system, the amount of force that is being applied in this direction, same amount of force is being applied in this direction. So again it is moving exactly, it is moving about this point, okay,
Yes,
right?
sir. And
Now,
it will
right,
be zero.
right. So effectively this point is not moving at all, right? This point will not
Yeah,
move, right?
yeah, middle point. Yeah, yeah,
This
fine,
point
sir.
will never move, right? This point will be
Yeah,
fixed, and this will move, right? The two ends will move, correct? The
yes,
middle
sir.
point
It
will
will
move.
vary there.
And
Yes.
now see, about the middle point, the both the sides are exactly antisymmetric, isn't it?
Yes, sir.
Correct.
Anti-symmetric. Yeah,
I mean,
fine.
the forces are antisymmetric. Correct.
Yeah, forces are anti-symmetric.
Correct.
Fine.
The sides are symmetric. True. The sides are exactly symmetric here, but forces are antisymmetric. Correct. So what I'm
Yes,
saying
sir.
now, let's say, yeah. Now let's say this this fulcrum, this thing here is not very well put. Okay, this fulcrum is not very good, and so what can happen is, now let's say two people are again sitting here. Okay, but both have different weights. So let's say this is a heavy person. Okay, and this is a very this has a low weight. Now what will happen? It will move in this direction. Okay, but over that, this will also tend to move down, right?
Yes, sir.
I mean, if this is not
Okay.
a very this is not fixed very properly, then this will also try to move, isn't it?
It may vary. Yeah, sir.
Correct. So all these things are basically an analogy to what I'm going to speak next. Okay. So now let's come back to our circuit. Okay, let's come back to the circuit question. So we have this circuit here. We get this MOSFET. Okay, the MOSes. Little bit wrong. So this is the circuit here. Here is your NMOS. This is NMOS. This is a resistor. This is a resistor. This is a current source. Okay. Now this one is some bias. Okay. Let's say this transistor and this transistor are sized the same. They are exactly same. Okay. Transistor M3 and M4 are exactly same. This transistor
Yes, sir. Identical.
this transistor M1 is identical with M2. Okay. Correct.
Yes,
Now
sir.
you can identify there is a point. There is a axis of symmetry here, right? What is the axis of symmetry here?
WL.
Axis of symmetry. I mean, about which axis you can say that okay, this is exactly the same as that they are basically mirror images of each other.
Yes, sir. M1 and M2.
Yeah. So basically, this is the axis, isn't it?
Yes, sir.
So
Yeah.
if you put a mirror here, both will look like the same, right? And if you
Yes,
fold
sir.
it around, basically if you take this part, cut this part and fold it back here, they will be exactly overlapping, isn't it? There will be no
Exactly.
mismatch. Correct?
Yes. Hmm.
Correct. So you see, in that case, if you whenever you find a axis of symmetry in a circuit, what happens is that uh, basically for differential let's talk about two different cases. Okay, for differential inputs and for common mode inputs. So you know this concept, right? That any
Yes.
signal, any two input signal can be split into differential mode and common mode, right?
Yes. Yes, sir.
Correct.
Yes, sir.
So now let's talk about two different cases. Basically for differential input and output, and differential and common mode input and output. Okay. So whenever you find such a circuit where you can find an axis of symmetry, okay, what happens is that for those circuits, if you apply a differential voltage, uh, basically a V plus here and V minus here, okay, what happens is this anything that is lying on this axis of symmetry will not move at all. Okay, will not vary. It will never vary. Okay. So what I'm saying is anything which lies on this axis of symmetry at any voltage, any terminal which lies as this at this axis of symmetry, it will never move. So what is another term for a voltage which is never changing?
I mean, means voltage will never changing means when voltage is difference is not equal to zero, sir.
Yeah, yeah, true. I mean, you are familiar. You know this term, right? I mean, if a voltage is never changing, okay, even if you apply, right. So let's talk about let's take a circuit, and in this circuit you have applied some excitation, okay, but even with this excitation, some part of the circuit is some in some part of the circuit the voltage is not changing at all. So what do you call that terminal? Anyone? What do you call that terminal where the voltage is not changing even if you apply an input?
AC ground, sir.
Correct. It is an AC ground. Correct. It can be called as an AC ground, right? Or small signal ground, because or in other words you can say it is a DC, right? DC is what? It never changes, isn't it?
Yeah, steady state, sir.
Steady state.
Yeah.
It never changes. So similarly, anything which lies on this axis of symmetry, any voltage which intersects with this axis of symmetry will never change. Or in other words, they will be small signal ground. Okay, they will be small signal ground like this. Okay, this terminal also, it will also be a small signal ground. Okay,
Yes, sir.
sure. And
I'm
this
following,
is
sir.
for differential mode operation. Okay, now let's talk about common mode operation. So this is differential mode. Let's remove this. Yeah, it's differential mode. Now next let's talk about common mode. What happens to the common mode circuit? Okay, again. So now you have found out what is the region of what is the axis of symmetry. Okay, now what you can do is whenever you apply a common mode signal, okay, to such a circuit where you have an axis of symmetry, you can basically, you see in this case also, if this circuit is symmetric about this particular axis, okay, if the circuit is symmetric about this particular axis, and you have applied the same input at both its terminal, okay, you have applied the same excitation at both the sides, right? The circuit is symmetric about this particular axis here. So basically whatever circuit is here, exactly the same circuit will be here also, right?
Yes, sir.
Moreover, you have also applied the same type of excitation at both parts of the circuits. So what do you expect to see in that case? What should happen to
So
this?
same output voltage each
Correct,
node, like.
correct. So basically, all the voltages here, because of this input here, all the voltages that will change in the circuit will change exactly the same way for both the parts, right? So whatever happens here, same thing will happen here also. So I may as well remove this part. I may as well remove this part and only be concerned about what is happening in this part. I can remove this part and only be concerned about what is happening in this, because exactly the same thing will be happening here, right?
Yes, sir. It's better, right?
Right now, you
Mm.
understand? So this is exactly what is common mode and differential mode circuits. So in this case, how do you solve so basically, now when you find the region of axis of symmetry, you first after that you analyze your circuit differently for differential mode operation and common mode operation. Okay,
Yes, sir.
and for common mode operation, you construct the common mode half circuit. So let's see what is that.
M3 and M1 away.
Right. Let's see. You see, in this case, let's say this current source was not a current source but a resistor here, right? Some resistor R. Okay. So what you will do is, the half of this will look like what? First, this R has to also divide, right, equally. So
R by 2. Yeah.
this part should get how much? Tell me. If you divide R equally and you are
R by 2,
making a
sir.
parallel combination here, so what should these individual values be?
Okay.
2R, right?
2 hour,
Yes.
2 hour, yes.
Correct?
Yeah. If it is series, the R by 2, no, sir?
Yeah, if it would have been series, right? But here there was a single resistor here, right, of R, and you have
Yes, sir.
divided
Yes.
it into two different resistors of two resistors of and you have connected them in parallel. So individually they should be 2R, right?
Yes,
So
sir.
that
Correct, sir.
after combining this becomes R, right? Now you can
Yes.
split it into two equal halves. And how will that look? So the half, common mode half, will be looking something of this kind. So you have this PMOS here, okay, and then you have this NMOS here. After that you have this resistor here, RX. So this is RX means again
In series with 2R.
in series with 2R here, right? And this is ACM, and this is the output that you are concerned with. This will be what? This was connected to some bias voltage, right? So what should happen to this in AC picture, small signal?
Bias
It will
voltage
be
will
AC
also be.
grounded, right? It will be AC grounded,
Yes, sir. Yeah, for this. Yeah, correct. Correct.
right? So this is what is common mode half, and this is differential mode for differential mode operation. What will the what how will it look for differential mode operation? It will look something like this. So you simply put everything there, but put a ground necessary places. So this will be grounded, okay. Moreover, this here is RX. This will be grounded here. We have RX again, and this will look something like this, okay.
Yes, sir.
Right. So this is how you have to proceed with any question where you find there is an axis of symmetry. Okay, you construct different equivalent circuits for differential mode operation and common mode operation, and then find out what is happening. So now let's talk about the circuit which is given in the question. Right. So the circuit was this, right? Let's put the whole thing here. Yeah. Fine. So now tell me what will be the differential mode gain? I mean, how will you find out differential mode gain? First, we have to construct the differential mode equivalent, isn't it?
Yes, sir.
So what all places will be AC ground here?
Yes.
Yeah, what all places will be AC ground here?
V bias, sir.
Yeah, correct. So let's construct. So construct differential. So we have this. This is M3, right? This
M3,
is
M4.
M4, and then
Yes.
this is ground.
Brown.
Correct.
Yes.
Now we have this M1.
Yes, sir.
We have some VI. We
Yes.
have M1. We have RX.
Yes, sir. And I bias. It's grounded. Bias is grounded, right?
Correct.
Yeah.
So this will be grounded, isn't it?
Yes, sir.
So this place will be grounded. Okay.
Yes, sir. And RX and M2 resistor.
Correct.
Yes, sir.
And we have this input. So this will be minus VI. Correct.
Yes, sir.
Fine. So this is what? This is M3. This is M4. This is M1. This is M2. So a few minutes earlier, some one of your colleagues said that the gain of the circuit will be what?
NSGM into RO3 parallel with the GM RO into
So
RX.
someone said this is the answer, right?
Yes. Yes, sir.
So now tell me, will it be true or is it not true?
We need to find out the gain, sir.
First of all, how what is meant by differential mode gain in this case? You have to find out V out divided by V plus minus V minus. Okay,
Yes, sir.
this is what you have to find. This is the differential mode gain, or let's call it let's A diff. Okay, let's call it A diff. Okay, so
Yes, sir.
what will it be?
Uh, for it would be we need to find out the equivalent transconductance.
Yeah. So what will the
Yeah.
equivalent
for for M1 and for M2 transconductance.
Yeah, this is, let's say, GM. Okay, let's say both have the same transconductance GM.
Yeah,
Okay,
identical. Hmm.
so what will the this thing be? The person who said the gain earlier, will you try? Would you like to revise your answer again? Would you like to revise your answer? I mean, is there something wrong with this answer?
Amit Potter.
Okay, fine. So let's see. You see that this transistor's GM is actually equal to GM, but that is not the GM that will appear as a whole here. This is a source degenerated transistor, isn't it? This is in source degenerated configuration. So what will be the effective GM in that case?
Sir, GM by 2.
Eh? GM by
Like
2. Why should it be GM by 2? Tell me what will be the.
actually, sir, if the DC bias tail current is I naught, then both of the transistor will carry I naught by 2.
Okay.
So
So no, tell me what will be the
so
description of the equivalent GM of this circuit.
sir, the total circuit is having two halves.
Correct.
So for the
Tell me. Okay. Okay. One second. One
M,
second. One second. One second. Let's go slowly. So this is one half. Okay. Basically, we will have to use superposition, isn't it? We will have to use principle of superposition here. We'll have to take Vi and minus Vi one by one, isn't it? So let's do that. Put Vi first and calculate how much is the V out. So we have this Rx here. This is grounded, okay? We have Rx here and this is grounded. And this is also grounded because we have only focusing on uh, okay, fine. So let's focus. This will be also grounded. This will also be grounded. Now tell me what will be the V out here.
G.
What will be the V out here? Come on, come on, because this is already discussed many times. What is the gain here? What will be the V out value here? First, tell me what will be the V out due to this half.
That would be zero, sir.
Correct. So what should be the V out? Be only responsible. So only responsible person for maintaining V out is this, right? Now tell me what
Yes,
will
sir.
be
It
the
would
V
be
out
B.
due to Vi?
BI. Yeah,
What is
in
the
the
value?
right side. It's G. GM.
It's actually GM times divided by 1 plus GM Rx, right? That is the effective GM multiplied by whatever output resistance you have, right? So let's call this M3. So it has some output resistance RO3, okay, which will be in parallel with the cascode connection here, right? Cascoding here,
In,
here. That will be GM times RO1 times Rx. Okay, this is the V out due to this. Okay,
yes, sir.
correct?
Yes,
Times
sir.
times
Exactly.
Vi. So times Vi. This is the V out here. Hmm?
Mm.
Now what will be the V out similarly due to Vi? So this is due to Vi plus Vi. Now we have to find out V2 minus Vi.
Yes.
What will it be?
Only it would be difference in the magnitude itself, sir. Everything will be
There
same.
will be exactly it will be exactly opposite of this, isn't it?
Yes, sir.
V
Exactly.
out should be after this minus of GM
GM
times 1
1 plus
plus GM
GM
Rx
RX
into Vi into
RO. Sir, resistance
RO
will be changed.
parallel
RO GM RO uh,
times RO2
2.
into Rx, isn't it?
Yes, sir.
Correct. Now
Yes, sir.
assume that RO4 is equal to RO3 and RO1 equal to RO2. Fine. So what will be the effective V out? So total V out Q2 plus VIN minus VI. What will it be? You have to simply add these two, isn't it? I mean,
Yes.
subtract these two,
VA.
because you have to find out V out, V plus minus V minus, isn't it? So you have to subtract these two. Correct.
Yes, sir. GM.
Correct. That will be 2 times GM divided by 1 plus GM
RX
Rx into into
into VI into RO for research and
RO4
student
parallel GM times RO2 times
into
Rx. Okay.
yes, yes, sir.
Fine. So this is the and what will be the gain in that case? So what is gain is equal to A diff.
Not by V. Yeah.
Simply this Vi will go away, right?
Yes, sir. 2 GM by 1
That's
plus
okay.
GM direct.
That's okay. That's fine.
Hmm.
That is easy. Fine. Now, so you understood, right? The person who
Yes,
was
sir.
saying that this is the this is not the gain, right? You simply forgot about this register Rx here. That Rx will be degenerating it. Okay. Fine. So let's now talk about the common mode half.
Common. Yes, sir.
So we have the same circuit again, but now let's construct the common mode equivalent. So we have common mode half. So we have this circuit, right? We have this circuit. We have to construct its common mode half. So it should look like this, right? So put it here so that we have a reference. Fine. So tell me what will be the common mode circuit look like? Yeah. Tell me.
Yeah, we have to take mirrors are one part M3 and M1 RX
Yeah.
and
RX
grounded.
only. RX here only. Right. So we
Yes,
will
sir.
construct a mirror here, mirroring line here. Okay. Tell me what should be the common mode equivalent here.
Yeah,
I have
M3.
constructed a mirror here now. Tell me what should I do now?
Yes, sir. M3 M1 RX
Fine.
grounded, sir. VA is the input for M1.
So you are saying that we have to do this. We have to do this. This is M3. Okay.
M1
And
input
we
voltage.
have this M1 here. Okay. And we
Yeah,
have this RX here.
and grounded, sir.
Why do you say grounded?
I bias current is that much.
This is bias current, true, but I mean, okay, this is a bias current, right? So what
Yes,
happens
sir.
to the bias current? I mean, what happens to the bias? They are in the small signal picture. What do they? What happens to them?
In small signal analysis for when finding we'll don't do it, sir. For DC analysis we considered and we will two different approaches, sir.
Correct,
And
true. So what happens in the small signal picture to any current source?
uh, current source means current source will short circuit or voltage source will sorry open circuit, sir. I think.
Current should be open circuited, isn't it?
Yeah,
So
yeah,
what
open circuit.
the idea is that anything that is part of that is basically part of the bias has to be desensitized. Okay, any voltage source or any current source, they have to be desensitized. Okay, so if the voltage source, what is the purpose of a voltage source? It has to maintain a some potential difference between two terminals, isn't it? So
Yes,
if
sir.
there is a voltage source between these two terminals, there will be some fixed voltage difference, right? There is some fixed voltage difference V, correct?
Yes, sir.
So if
Like,
you want to desensitize this voltage source, what will you do? You will simply make it equal to zero, isn't it?
yes, sir. Then we do, yeah,
And
fine.
if you make V equal
Short
to zero
circuit.
between these two terminals, what is happening effectively here? The short circuit, isn't it?
Yes, sir.
Similarly, if you have a current source between two terminals, what is the purpose of current source? Its purpose is to make sure that a current I naught flows here, right?
One direction. Yeah,
Right.
fine. Yes.
Now, if you have to desensitize or make its purpose make it purposeless, what will you do?
Open circuit, sir.
You will have to make sure that I naught is zero, isn't it?
Yes, sir.
And what is meant by n equal to zero? Which is meant by no current is flowing between these two terminals, right? Which is
Yes, sir.
basically the same thing as saying that these are open circuited,
Yeah, yeah,
right?
correct.
And here it is short circuited. So any voltage source is short circuited, any current source is open circuited. Okay, fine. So now, so basically, what should happen here?
Yeah, the die bias is open circuited, sir.
Okay, so this I bias, oh, sorry, this I bias here is open circuited. So
Open.
there is nothing here, right? And then there
There
is
is no
current,
flow current in that direction. Yeah, there is
correct?
no current flow in RX also, I think.
Correct.
Yes,
So
sir.
that's what. So
50%.
basically, because there is no path here, right? There is no path here. So no current can
Yes, sir.
flow through here. This like this, right?
Yes.
So in the common mode, we have this circuit. So in the common mode, what is the circuit? This is the circuit. We have some VCM here, and then there is RX, but then there is open circuit here, right? And this will be grounded. This V bias will be grounded because this is a voltage source, isn't it? So this voltage source should be grounded, isn't it?
Yes, sir. The
Right?
current will be flow into the ground path only. Yeah.
No, there can be no current, right? So if there is no current flowing in this here, no current
Mm.
can flow through this here, no current can flow through this here, so no current can flow through this here, right?
Yeah, yeah, yes, sir. Yes, sir.
Yeah. So basically, what is the common mode gain in that case? What is the gain between this and this? If you apply anything here, will it move? I mean, will V out change?
Nothing, sir. It would remain same,
Correct,
saturated.
because there is no current flowing here, right?
Yes, sir.
Common mode gain here is how much?
V out is equal to V in
I mean, V out
uh,
by
V
VCM,
in.
correct?
Yes, yes.
That is equal to zero, isn't it? Because whatever VCM you put here, V out will always be zero. Okay, so that is why common mode gain here is zero. Is that understood?
Yes, sir.
Cool, cool. So
Sir, irrespective of VCM, what and all value we give, the output, that gain remains will be zero.
yeah, it doesn't matter if you put anything here, if you put any voltage here, because this no current is flowing here, right? I mean,
Yes, sir.
just understand it in this manner that there is no current flowing here at all in this direction. So no current can flow through this transistor also, right? So this voltage here can only change if there is some current change, isn't it? If the current is not changing in this branch here, how can the voltage change here? It cannot. It can never change, isn't it?
Yes, sir. Yes, sir. Correct, sir.
Right. So whatever voltage you put here, whatever VCM you give here, it will never change. This V out is never going to change,
Yes, sir.
right? So what basically? So let me ask. Go ahead and ask this question to you. So you are changing something at one of the terminal of this MOSFET, right? You are let's
Yes,
say it
gate
is
terminal.
VCM here. So
Uh,
but V out is never changing. So but you know this relation, right? That current I is equal to VGS minus VTH whole square times W by L times 1 over 2 times mu n C
Yes, sir.
off.
Mu saturation is
Right?
drain current. Yes,
Right? This
yes,
is
sir.
the drain current. Right?
Yes, sir.
So, if this VCM is changing but there is no current flowing here, so what should happen? Tell me. What happens to
Yeah,
this voltage, this terminal here? Let's call it Vx or yeah, let's call it Vx and let's call it Vs. So if
okay.
VCM is increasing here, what should happen to Vs and Vx?
Yeah. See,
Anyone? So this question, I'm asking
It
you.
should increase, no? Vx should increase.
What? Go ahead.
Uh, because like that's how we can minimize this difference. Because current is constant, na, and
Current is zero.
V on
Zero.
is
It's
increasing.
a simple zero. Current is zero. So tell me. I mean, incremental current is zero. Okay. Incremental current is zero. If you increase VCM, yeah, correct. So sorry. My bad. Current is a constant here. Okay. Current is a constant here. It is I how much? I bias by 2. So it is flowing in both of this, right? Both of this, the current is I bias by 2, isn't it?
yes, sir. If it is balanced,
Yeah, it is balanced. So,
yes, sir.
uh, so I will be confusing you. So let's take a step back, okay, and concentrate here. So in this case, I am saying that this is basically a small signal picture, okay. This VCM, I am putting a small signal here, okay. There is some bias put here. Over that, I am putting some small signal, which is a common mode for both, okay. Now for that common mode, the this is open circuited, isn't it? So if this VCM, if it increases slightly, what should happen to this terminal Vx and Vs if the current is zero here? There is no current flowing here, isn't it?
Yes, sir. Yeah, yes, sir. But I mean, that potential difference will be may vary. So, no, sir. VGS, we are applying voltage to the
Yeah,
gate terminal,
yeah,
and source terminal is open circuited, right?
correct. So what should
Yeah,
happen?
yeah, open circuited. What with respect to the value that remains will be same, sir.
So yeah, so are you saying that this VCM minus Vs should always be same, isn't it? You are saying. You
Yes,
are
sir.
saying.
Yes, VS is open circuited side, right? No, sir.
Right.
VS is
So
connected
so
to
I'm
open circuit.
so are you saying that if I increase VCM, Vs should also increase? You are saying in the same manner, in
No, no,
exactly the
sir.
same amount.
No, sir. That
Then
won't be, won't be changed. No, sir. That is open circuited, right? If it is short circuited, the potential difference may vary.
right. You are saying
Mm,
correct. So I'm
mm,
saying that
mm.
this you know that there is no current flowing here, right? There is no current
Yes,
flowing
sir.
here, correct?
Yes, sir.
So
Yes, sir.
this
Current is
resistor
zero.
Rx has no current basically flowing through it, isn't it?
Yeah, it would be discarded.
Correct. So if there is no
Mm,
current flowing through a resistor, what is the difference
mm.
between? So if there is this is a resistor, this is one terminal which is at Vs, this is one terminal which is at Vx, right? So there is
Yes,
no
sir.
current flowing through it. So what is Vx
Mm.
and Vs? The relation,
Exactly equal, sir.
correct?
E-
Vs should be equal to Vx, isn't it?
Yes, sir.
Now
Yes, sir.
similarly,
Then only, yeah, current would be zero. Correct,
correct.
correct,
If
correct. Yeah.
there is no current flowing through Rx, so this relation holds. Vs and Vx are equal to each other, right?
Yeah. Yes, sir.
Again,
Open circuit. Yeah, got it.
again,
It,
in the same manner, we
mm.
have a relationship for a current flowing through a transistor, right? If this is a transistor, correct? Sorry, if this is a transistor, and this is the Vs, this is
G.
Vg,
Yeah.
okay.
Yes.
And in the small signal, let's not talk about this, okay. Let's forget about
Mm.
this. In the small signal, what is the current flowing through this? Gm times Vgs, isn't it?
Yes, sir.
Right now, you have this picture, right? This is Vg, and this is drain,
GM into.
correct? So
Mm.
this is Gm times Vg S, right? This is Vs, correct? So you know that the current flowing in the MOSFET I is equal to Gm times Vgs, right? But now I am saying
Mm.
that now you only said that in this particular MOSFET here, right? The current is zero, correct?
Yes, sir.
There can be no current flowing here, right? So tell me, if the current is zero, what should be Vg and Vs relation?
It would be same, sir.
Equals here.
Correct. So they should be equal to each other, right? Because VGS has to be equal to 0. So VG has to be equal to VS, isn't it?
Yes, sir.
Yes.
What I am
Yeah.
trying to get at here is that when you increase VCM here, right, V out is
Hmm.
not changing, okay, but Vx and Vs are changing, okay. The moment
Hmm.
you increase VCM here, Vs will also increase in the same manner, okay. Let's say you
Yes.
increase VCM by 1 volt, VCM will also increase by Vs will also increase by 1 volt, Vx will also increase by 1 volt, okay. Only then
Yes.
can you ensure that there is no current flowing through this transistor here, isn't it?
Yes, sir.
Yes.
Yes, sir. While mathematically also, while substituting the current equal to zero, and after all substituting the values,
Correct, correct. You will
VGS.
get the same thing. But I am
Yes, sir.
trying, just trying to motivate, give you an intuition here, because no current is flowing. So you know this circuit, right? This is a
Yes,
very
sir.
famous circuit. So this is the same as this. You know what is a? So you have heard about the source follower,
Yes, sir.
or in other words, it is a common drain amplifier. What is that? You have a resistor here. Let's say R. Okay, or let's say you do not have a resistor, you have simply some V bias here, okay. Then you have a transistor here, okay, and you have a current source here, some I naught. You put your input here, you put your output here, you get your output here, okay. So what is this called? This is a common drain amplifier, isn't it?
Yes, sir.
Correct. And what is the gain between this and this? Zero, because there is a current source here, isn't it? It is the same
Yes,
circuit as
sir.
this. It is exactly the same as this here. In the small signal, this will simply open circuit, isn't it? And you cannot have any current flowing through this. Correct? So
Hmm.
whatever input you give, exactly the same output you will get. Right now.
Yes, sir.
So V in
Comment.
is equal to V out in this case. This is a source follower. So I'm just trying to give a feel of what you have already done. Anyway, so let's not confuse you anymore. Uh, Fine. So this circuit and basically this circuit and this circuit, you can I have solved the circuit here, so you can solve the circuit, isn't it? You can find the small signal common mode and differential gain here. How will you solve this? Because this is easy for you now. Tell me what will be the common differential mode gain here in the circuit of B.
Differential. Yes, sir. M3, M2, PI, M1, RX, open circuited, sir. Here, sir, here it won't be symmetrical, right? No, sir.
Why are you saying that it is not symmetrical?
Uh, it is, I mean, gate terminal is gate terminal and source terminal are short circuited, no, sir. That's why.
So what? Can you find there is a mirror symmetry or not? Can you find a mirror symmetry or not?
Yes, sir. This is symmetric.
Yes, this is symmetric indeed. This is the line of symmetry here also, isn't it?
Yeah.
You see, this and this part are exactly same as each other.
Okay. Yeah, sir. Okay,
Correct?
okay. Hmm.
Fine. So these two are
If
common.
one is not short circuited, then may that
Correct.
symmetry.
So then there is no symmetry. True. If this
Mm,
would have been like this, then it
mm,
would have not been symmetric. Okay.
yes, sir.
This is not a symmetric circuit. You cannot do that analysis anymore. But here that is not the case. Here you have what?
Yeah, short circuited, sir.
Correct. So you have a
Yes, sir.
symmetry here. So what is the gain now? Differential mode gain.
Uh,
First of all, tell
yeah.
me what is the common mode gain here between input and output. So output is again here. Okay. What is the common mode gain?
Common mode. Yes, sir. Right, sir.
Again the same thing. Do the exact same thing. How will you do the common mode gain here? First you will break the circuit, isn't it?
Yes, sir. M2 and M1 and input voltage RX and it is open circuited, right?
1 second. So this is M3 dot M2. This is
Yes.
M3. Then you have M1. Then there is RX, and then there is a what is?
Open,
Closed or open?
open circuited, sir.
Correct.
Bias
This
voltage.
this will be open circuited, isn't it? For
Yes, sir.
common mode operations. Okay.
Yes.
So tell me
Yes, sir.
what will be the, if this is open circuited, what will be the current flowing here?
Zero, sir.
Right. It will be
Gain will
zero.
be, yeah, yeah, zero. Output gain will be zero, sir.
Correct. It will be zero here.
Yes.
Now tell me what will be the differential mode gain?
It's a definition mode. Yes. On open circuit.
Okay. Tell me what will happen to every. See, every
Yeah.
point that this line is touching,
First, we
all the
find out
inputs
the
will be
at post
grounded.
what's post. Yes, sir. At while finding V place, it would be yes. RX.
Yeah. Tell me. So
Yeah, sir. G will
what
mean
will
to G.
happen to this? What will happen to this?
Uh, yeah, which one, sir? Bias current or what?
This
Not.
terminal. This terminal. What will happen to it?
Oh, yeah, both are symmetrical, no, sir.
Yeah. Correct.
Yeah, symmetrical. First, we find out M1. I mean, first side V plus and second side, and then we will find out the gain, right?
I mean,
That's the
what
procedure.
I'm not asking that. So I'm asking what will happen to the to this terminal in the differential mode equivalent. So in common mode, you said that this will be hanging, right? This will be open circuit here, and this will simply hang, correct?
Yes,
But I'm asking what will happen to this terminal in the differential mode equivalent.
that output voltage, sir.
No, no, this terminal.
And it's not showing, sir, that what you are writing. The change is not visible.
Ah, okay. I'm asking about this.
Oh, okay, okay. Here, okay, fine, fine. Yes.
What will happen to it in the differential mode?
Yeah, it will differential mode.
Okay, so I
Yeah.
guess you are confused. Okay, so don't get confused. Okay, don't get
Yes.
confused. You see this that as I already talked about in this circuit. This is the example that I told about, right? So you see
Yes, sir.
in this circuit, you see there is a mirror symmetry, isn't it? Exactly in the half here, there is a mirror symmetry. So anything
Yes, sir.
which lies in the on that axis of mirror symmetry, that will become a short circuit AC ground for the differential mode operation. Okay, that is only true for differential mode operation. So whenever there is a differential mode operation, you are talking about differential mode operation. In that
Yes,
case,
sir.
anything which lies on this axis of symmetry will become this ground. Okay,
Yes, sir.
this is
Yeah,
true.
yeah, got it, sir. Yes.
But for the
Mm.
common mode, yeah. So for the common mode, that does not hold. Okay, don't
Yes,
use
sir.
the same thing for common mode.
Yes, sir.
For
Understood.
common
Yeah,
mode,
what I commit a mistake means that bias current will be grounded, sir, here for
correct. Here it will be
differential
bias
mode.
current will not be grounded. This terminal will be grounded. Okay, this terminal will
Yeah.
be grounded.
Yes, yes. So that symmetric point where we are
Yeah, yeah,
finding the
correct.
symmetry,
Bias
that will
current
be
will
grounded.
always be open circuited in the
Mm.
in the small signal picture. Okay, this will
Yes,
be
sir.
open circuited even in the differential mode half, but that doesn't
Mm.
matter anyway, right? Because this point will be AC grounded, isn't it?
Yeah. Yes, sir. Yes, sir. Yes, sir. Got it.
So after that
Yes.
you can find the gain in the exactly the same manner as earlier.
Mm.
So exactly same manner as this case,
Yes.
right? As this case, fine. So let's
Yes,
move
sir.
on to the next problem. So is this clear, by the way? You understood?
Exactly, sir. 100%.
Okay, okay, fine. Let's move on. Okay, this is for you to solve. Yeah. Now let's talk about ranges. Okay, important one more range. That is important question to discuss. Fine. So yeah, tell me. A current I naught is flowing here. Okay, and so how much current should flow in this and this?
Yeah, if both are identical, that current will be divided, circuit will divide I naught by 2, I naught by 2.
Current. So current will be current through
M1 and M2 will be I naught by 2.
Current through M1 and M2 is what?
I naught by 2, sir.
And what is enforcing this condition in this circuit? It is these two are not identical minded. So what there is something else which is enforcing this condition that these two currents should be equal. The current flowing in this branch and in this branch should be equal. Who is enforcing that condition?
Symmetrical, sir. I mean, it should be identical.
Why
That
is it
M1
not
and
symmetrical?
M2
Why,
are
how
not
it is?
symmetrical, sir. Oh, no, sorry, sir. Not symmetrical, sir. Identical, sir. M1 and M2 should be identical. Then only that
Yeah,
current will
identical,
be.
true. But even then,
Current mirror circuit.
correct. So there is a current mirror circuit, isn't it?
Yeah.
This is a current mirror, right? So what is the
Yeah.
purpose of a current mirror?
Current.
You have do you know what is a current mirror?
Yes, sir. Yes, sir. I'm just. I want to recall. Yeah.
Correct. So the
Um,
purpose of a current mirror is this. Okay, let me help you recall. So this is a current mirror. Okay. So
the
whatever
input
the
current
flowing,
and output current should be same, sir.
correct.
Yeah.
So whatever current is flowing here I naught, same
Mm.
current will flow here I naught if the sizes are same. Okay. So this is W by L and this is also W by L. Same current should flow in both the transistors. Okay. That is the purpose of a current mirror. Okay.
Yes, sir. Yes, sir.
Fine. So in this case, the guy that is the thing that is ensuring both the currents should be same will be are this. Okay, this M3 and M4 because they are current mirror. Okay, and over on top of that, these two currents should be equal. On top of that, who is making that again possible? As you said, as you correctly said earlier, that these two transistors are also identical. Okay, M1 and M2. Okay, and they have the same voltage at their input, VCM, VCM, right?
Yes,
So
sir.
the overdrive here and overdrive here are exactly the same because this is again common for both of these, right?
Yes, sir. Common
So
node.
VCM minus Vx is same as VCM minus Vx for M2 also. For M1 and M2 both, the overdrive is exactly the same. So there can be no other current but I naught by 2 flowing through each of these branches. Moreover, can you say something about this about this voltage V out? And can you say some any relation between V out and let's call it V out prime? So can you say anything about V out and V out prime? V out hat? Is there any relation between V out and V out hat here?
Yes, sir. V out is equal to V out hat plus that one more drop voltage will also get added, sir, while we are
How come?
calculating.
How come? Why?
Not this, sir. Similar kind of current mirror is all in previous weeks.
No, no, no. This is just a
Uh,
thing from basics. Okay. What is the?
yeah.
I'm asking. Can there be? Is there any relation between V out and V out hat? Assume that there are some output resistance here and there. Okay. That will help you. So let me simplify this image. Enlarge this image. Okay. So you tell me, is there a relation between V out and V out hat here?
So if M1 and M2 are equal, then V out and V out dash will be equal now, I guess.
Yeah. So how? Why are you saying that?
Because if like same load is there on M3 and M4.
Sir, drain terminal is grounded to drain terminal is short circuited to gate terminal, sir. That's why.
That is here, but
Yes.
there is nothing in between these two, right?
Yes, sir. Yes, sir.
So yeah, so other guy, what were you saying?
Nothing, just V out and V dash will be equal because like M1 and M2 are equal.
So
So
I'm sorry, I cannot hear you. I mean, can you please speak up, please?
yeah, actually, I was saying if M1 and M2 are equal, then there should be
Uh-huh.
like equal load on M3 and M4. Then those V out dash and V out are equal, I guess.
Okay, now let's see. So for your purpose only, I told you to, for this only, I told you to assume that there is some output resistance here. Okay,
Okay.
and let's say there is some output resistance here also, in between these two also. So you have this and you have this. Okay, these
Okay.
are some output resistance. Now tell me, now can you easily say? You are right. It is. It will be true. V out is will be equal to V out hat. But why? I mean, give me a concrete, more concrete, this thing explanation. You see this I not here. First of all,
Yes. Yeah, sir. I
these two
get a one
currents
idea.
should be exactly same, right?
Yes.
This is making sure that the current is exactly same, right?
Yes, sir.
Now for these two halves, for these two parts, the only thing. Okay, so let's see. For these two halves, the gate is this gate is common for both the halves, right? This both this NMOS and this NMOS, right? Gate is common for both of them. So VGS will be same for both of these, right?
Yes, sir.
Correct? Right now,
Yes, sir.
this VGS is same for both of these. So because of VGS, same current should flow here. Correct? Right?
Yes, sir.
But now, where can the difference come between currents? In between these two currents?
Yes,
Only
sir.
because
Here.
of the
Yeah.
difference can come only because of this resistance R. Let's say this is RO4 and this is RO3, right? If the voltages between these two, if V out and V out hat are not equal to each other, then only and only then can there be a current mismatch between these two, right?
Yes, sir.
Yes,
Yeah.
sir.
Right. Now let's say there is a current mismatch between these two, correct? And for simplicity, let's assume that V out is greater than V out hat. Okay, if V out is greater than V out hat, this current this current should be larger than this current, isn't it? So this is very messy now. It's very messy. So here another color. So let's call this current as I2 and this current as I1. Okay, if V out is greater than V out hat, what will be the I out? I out will be definitely greater than I1, right? It should be because of this NMOS, right?
Yes, sir.
I mean, we know that, right? This is simple. This is channel length modulation. Okay, so RO4, if there is RO4 and RO3, if I2 is greater than if V out is greater than V out hat, then I2 will be greater than I1, right? Due to this condition that I have enforced on NMOS, correct?
Yes, sir.
Right. Now, if I2 is greater than I1, in that case, and V out is greater than V out 1, V out hat, right? Correct? But here you see, for the PMOS, both the PMOS gates are exactly at the same potential and their source is also exactly at the same potential, isn't it? So for them, overdrive is again the same, isn't it?
Yes, sir.
So current flowing
Equal
through
to
their
zero.
through them will should be same, isn't it? So the only difference that in the current that can happen, that can come through, is because of this these resistances, right? RO1 and RO2, correct?
Yeah, that will vary. Yes, sir.
I mean, because of this only, it can there can be difference in currents, correct? Now what? Now let's see. I have already assumed that V out is greater than V out hat, right? And because of that, NMOS was telling me that I2 should be greater than I1, right? This relation should hold if V out is greater than V out hat. Okay. this relation should hold for the NMOS to work properly. But if this condition holds, if V out is greater than V out hat, if V out is greater than V out hat, what will the PMOS tell me?
Yeah, that M2, it may vary, sir. That voltage difference, that M2 will be greater than M1. That VCM across.
No, no,
Okay.
these
Uh,
voltages are fixed. I mean, this are same. This VCM is fixed. This Vx is fixed. Okay. So what
okay.
I'm saying is, I2 and I1 current are flowing through this these two transistors. Okay. Okay. So maybe I'm not drawing it properly. So this. So what I'm saying is, let's assume that the current flowing through this in this bottom half, okay, is this. This is I1, okay. This is I2, okay. This is bottom half current, okay, right. Now current flowing through the top half. Let's also consider current flowing through top half, okay. Already I have found out what is the relation between I2 and I1. I2 should be greater than I1 because V out is greater than V out hat, that I have assumed, okay. Now let's focus on the top half here. If V out is greater than V out hat, which and let's say this current is current flowing through this side is I2 I2 prime, okay, and current flowing through this side is I1 prime, okay. So tell me, which current should be larger here, I2 prime or I1 prime? If V out is greater than V out hat,
I1 prime, sir.
I1 prime should be larger, right?
Larger.
So I1 prime should be larger than I2 prime, correct? Now you see the contradiction here. I mean, you see that whatever current is flowing here, same current should come from up also, right? So I2 prime should be equal to I2, isn't it? I mean, where will the current go, right?
Yes, yes, sir.
Right
Yes.
now,
Hmm.
current has nowhere else to go. So if there's something is coming from here, it should go here, right? So
Yes.
I2 hat should be equal to what? I2 prime should be equal to I2, isn't it? And similarly, I1 prime should be equal to I1, isn't it? So you see the contradiction here. I1 prime, I have assumed earlier here, it is saying that I2 is greater than I1 for the for the NMOS case. But on the top, I'm getting this condition that I1 prime is greater than I2 prime. So clearly, it's a contradiction, isn't it? Because I1 is at that I1 prime is equal to I1 and I2 prime is equal to I2. So both have to be, they cannot be greater than or less than. They have to be exactly equal to each other. I2 should be equal to I1 and I2 prime should be equal to I1 prime. Is that understood by you? Other people? Or was it too convoluted to understand?
Sir, understood.
Yeah, so the person who was saying that I2 is equal to I1, sorry, V out is equal to V out hat here. Similarly, you can, so here I have proved that I2 is equal to I1, but similarly you can say that V out is also equal to V out hat, okay, in the same manner. So now is that understood by you? The person who was saying earlier V out is
Yes,
equal
sir.
to V
Yes,
out
sir.
hat.
Yes,
You
sir.
were right, right? Okay, you were right, but it's just that this is a more concrete way of proving it. Okay,
Okay, sir.
fine. So you were right. You were exactly correct. So that is the correct answer. Fine. So okay. So that was. Let's get back to the question. Yeah. Fine. So yeah, I have to find now the. So basically here, current I naught by 2 is flowing in each branch, and V out should be equal output V out hat, right? Correct. Now tell me what should be the input common mode range. So how much VCM can go? How low can VCM go? So what is meant by input common mode range? It basically means that what can be the largest and minimum what is the highest maximum and minimum value of these quantities. Okay. Tell me, so what is the this is V out. Fine. So tell me, what is the minimum value of minimum of VCM? How will you calculate that? How will you calculate minimum value of VCM? This was covered in this week's lectures, right? How will you calculate minimum value of VCM so that all the transistors remain in saturation? Okay, fine. So now let's see what will happen if VCM starts to go down. Both are VCM, right? So what will happen if VCM goes down?
That I will not by 2 will be reduces, sir. The current will be
Why that should reduce? I naught by 2, why should it reduce? Again, I naught by 2 is enforced by these two, right?
yes, yes sir, yes sir.
So why should it reduce? It should not reduce, isn't it? For I naught by 2 current to flow in between in these two branches, I naught by 2, there will be some voltage here, right? There
Yes,
should be some overdrive here, correct?
yes sir, VGS, yeah, get
Correct?
to,
There should be some
yes,
VGS here. Fine. So same value will be here also. Let's call it V. Let's call it VB. Okay. Let's call it VB1. So similarly, this voltage will be VB1, isn't it? And if this is VB1, this will be also VB1, isn't it?
yes sir.
Fine. Now tell me what will happen if VCM starts to go down. What will be the problem? I mean, which transistor can go out of saturation? Which transistors has the possibility of going out of saturation?
Yeah, Woodford sir.
M4.
Yes sir.
How come?
How come? Yeah, here drain terminal and gate terminal shorted no sir. So
So what? If this goes down, and
yeah,
so okay, so let me ask you this.
yes,
So what is the condition for going to linear region?
yes sir. That VDS is equal to should be less than or equal to VGS minus VT sir. If it is greater than, then it would be yes sir. Less than, yeah.
Correct?
It would be in a resistor region. Yeah.
Right. So if it has to stay away from it, then VDS should be greater than, right, or equal to VGS minus
Minus.
VTH.
Yes sir.
Correct?
Yeah. Fine. Yeah. Yes sir.
Right?
Yeah. Yeah.
This is saturation. Correct? Now tell
Yes
me,
sir.
uh, what is the drain to source voltage of this M4?
VB VB1.
Correct?
Yes sir.
Right? Now is VB1 dependent upon VCM in any manner?
No sir.
What is VB1? How will you find VB1? So VB1
From
will be VB1 minus VTH the whole square times W by L is equal to
Views.
mu n Cox is equal to I naught by 2, isn't it?
Yes, sir.
So from here you will find VB1, isn't it? So VB1 is not dependent upon VCM, isn't it?
Yes, sir.
Correct? So,
Yes, sir.
so what happens if VCM goes down? M4 does not, nothing happens to M4, isn't it?
Yes, sir.
Because
Yes,
its
sir.
VDS is not changing. If it is in
Yeah, yeah,
saturation, then it will
yeah,
remain in saturation. Okay?
yeah.
Fine. So similarly, what happens to M3?
Okay, it is.
This is easy, right? M3 is all M3 will can never go out of saturation because it is diode connected, isn't it? Its VDS is always equal to VGS, right?
Yes, sir. Yes, sir.
So for
Here also, sir.
M3, uh, first for M4, nothing happens if VCM goes down. Correct? Now for M3, always in saturation since VDS is always equal to VGS, isn't it? So VDS will always be greater than VGS minus VH.
Infinity.
Correct?
Yes, sir.
Correct. Now tell me, so M4 and M3 are safe, isn't it? If VCM goes down. So what happens to M1 and M2? No, first of all, what happens to M0 if VCM goes down?
There is no relation between a. Yeah. Oh yeah, fine, fine, sir. Yeah, yeah. That gate voltage and source voltage is connected to VCM, no, sir. No,
Which
the
one you
source.
are you asking? So I'm asking about this M0, M1 and M2. Tell me,
Yes.
which one should I take first? M1? Let's talk
Yeah.
about M1.
Yeah, one, sir.
For M1. Okay, fine. So what happens to M1? Tell me. As VCM goes down, V out, this terminal, this drain terminal, does it change?
No, sir. We have to not change it.
So drain, when VCM goes down, uh, drain is fixed, right?
Yes, sir.
Fine. And what is the drain voltage? It is some VB1, isn't it?
Yes, sir.
So VD of M1 is equal to what? VB1. Okay, fine. What? So now drain does not move. Okay, gate goes down. So what happens to this source voltage? Vx. What happens to that?
Gate voltage is reducing, no, sir.
Yeah.
VGS will get reduced, sir.
What happens?
Yeah, VGS might be VGS will get reduces, no, sir. Gate voltage is reducing that VGS.
Why should VGS reduce?
Yeah,
So other
VCM
people,
is correct.
okay, hold on, sir. Other
Yeah.
people who are in this meeting, please participate. What happens if VCM goes down? What happens to the source voltage Vx here?
Vx doesn't change, sir,
Why shouldn't it change?
because it's changed, sir. Because VCM changing, the current is changing, sir. So that's why
Current will
Vx
change.
also change.
Okay, that's what. If VCM goes down or goes up, will that change the value of current which is flowing in these two
Yes, sir.
transistors?
Small increment current will change.
No, assume there is no output resistance here. Okay, there is no resistance here. M0 has infinite output resistance. Assume that. Okay, assume that M0 has infinite output resistance. Okay, so
Okay.
okay, one second. Tell me, if VCM was changing, does that change the current in this M3 and M4?
Current will not change, sir.
Current will not change in M3 and M4, right?
Yes, sir.
It should be I naught by 2 here and I naught by 2 here also. Okay,
Yeah.
fine.
Mm.
If this is I naught by 2 here and here, uh, will current change in M1 and M2?
No, sir.
Yeah, so why is it taking so much time? Same current is
No.
flowing, isn't it? This
Yes, sir.
current
Yes,
is
yes,
exactly
yes,
the same
yeah.
as this. So whatever happens
Yeah.
for M3 and M4, same thing happens for M1 and M2, right? Current cannot change. It is also containing I naught by 2. This is also containing I naught by 2. Fine? Fine, na?
Yes, sir. Yes, sir.
Fine.
No problem, sir.
Now
Yeah.
tell me, if the current is not flow, current through M1 and M2 is not changing and VCM is changing, so what happens to Vx?
VX also doesn't change, sir.
Okay, so let's ask this question here. What is the current through M1 dependent upon? What is the relation? What is the equation for that? Current through M1 half
Very
VCM
confused.
mu p Cox W over L, right? Times
VGS, yeah.
V what?
VGS minus
Vx
VT.
minus
Yeah, VX.
VCM
VCM
minus
minus VT.
VTHP, right?
Whole square.
Square,
Yes,
isn't
sir.
it? Now tell me, this current through M1 is equal to what? I naught by 2, isn't it? Always. It is not changing. But I am decreasing VCM.
Yeah.
VX increases, sir.
Vx increases.
Yes.
It should
I thought
increase.
it even has a NMOS, sir. I forgot. I forgot.
CMOS,
One
CMOS.
second.
Yes,
Why should Vx
sir.
increase? If it increases, if current through M1 is I naught by 2, it does not change. If VCM goes down, Vx also has to go down, right? Otherwise, this difference will increase, isn't it? If Vx increases, this difference will increase, isn't it? Vx minus VCM.
Both has to decrease to
Correct.
maintain the difference.
Correct.
Yes.
This difference has to remain constant, isn't it? Otherwise, current will change. So the current has to remain same, and that is why Vx minus VCM has to be equal, right? Always same. Vx minus VCM should always be the same value, isn't it? Guys,
Yes, sir. Yes. Then only it would be possible.
correct,
Possibility will
correct.
be.
So
Yes.
when
Current
VCM
will be
goes
same.
down, Vx also goes down by the same amount, isn't it?
Yes, sir.
Vx also goes down by the same amount. Mind it.
Yes, sir.
So that is
But
why,
VDP will be changed. Will be
correct. So
the
what
only.
happens now? VD, this drain voltage was not changing, that was fixed at VB1, but gate voltage VG is equal to what? VCM, correct?
Yes, sir.
And its source voltage Vx is equal to what?
VCM.
No, it is not VCM, but VCM plus some
Minus.
V threshold,
Uh,
right? And plus some overdrive also, plus some V overdrive. Okay, so one second. You are getting confused. So the equation is what? Current equation is what? I naught by 2 should be equal to mu p Cox W over L, correct? Plus, sorry, into 1 over 2 into
we
Vx minus VCM minus
plus
mod of
minus
VTHP
modulus of VDP. Whole square, sir.
whole square, right? Correct? So what
Yes,
should
sir.
it be? Tell me. What should Vx be? Vx is equal to what?
VCM
I naught by 2 into 2, so it's I naught into divided by mu p Cox W over L, correct? Under root plus, come on, what will it be? Vx will be what? Plus VCM plus VTHP, isn't it?
yes, sir.
Right now. So that is what I
Hmm.
have written here. VCM plus VTHP plus 2 I naught divided by, so not 2 naught, only I naught divided by mu p Cox
Hmm.
W over L, right?
Oh yeah.
This
Oh,
is
fine, fine.
Vx. what is the this thing? VG is VCM. This is right. So now tell me what should happen. What should be the relation? So you can clearly see that when VCM is going down here, this drain voltage is not changing, but this source voltage is also coming with it, right? It is also decreasing. So clearly, drain to source voltage is decreasing, isn't it?
Yeah, VDS. Yes, sir.
VSD is decreasing, but VGS is always the same. So this M1, it has the possibility of going to linear region, isn't it?
Yeah.
Because
Not only M2, other resistor, other MOSFET also possibilities there.
correct, correct. M1, M2 both are exactly the same.
Yes, sir. Yes.
Both have the same possibility. So for M1 or M2, okay.
Yes, sir.
What is the relation? What is the condition for linearity for PMOS?
VDS is less than VGS minus VT, sir. Modulus of
VDS,
VT. Yeah.
right,
Yeah. Yes. Yes.
is less than.
Yes. Yes.
Sorry, for straying away, it should be greater than VSG minus mod of VTHB,
Modulus of.
isn't it?
Yes, sir.
Right.
Yes.
Now clearly, VS is decreasing, VD is constant, and VSG is again a constant, right? So that you can now find the relation, right?
M1 and M2.
So what is
Mm.
VSD? VS is equal to VX, right? So Vx minus Vd of should be greater than what? Vs is equal to Vx minus Vg minus mod of VTHB. Correct? What is Vx? Vx is
Yes.
2
I not
I naught divided by
VC,
Vcox
uh,
W over L
W by L
plus Vcm
plus VCM plus
plus Vth,
modulus of VT. Yes.
right? Minus what
Mm.
is Vd? Vd is Vb1. Correct? Should be greater than
Yes, sir.
Vx is again
VX
Vd.
minus.
So this goes away here itself, right? Why should I write so much pain? So this is minus Vd should be greater than, or Vd is equal to what? Minus of Vb1 should be greater than minus Vg. What is Vg?
Yes, a minus minus will also get cancelled. Yes, sir.
Yeah, yeah. One second. We'll
Minus
come to that.
mm,
And minus mod of
mm,
VTHB, right?
HP.
Right?
Yeah. Yes.
Right now.
Yes.
So
VB1 should be greater than VCM
less
plus
than equal
VT.
to VCM plus mod of VTHB. Yeah. So sign flips, isn't it?
Yes, sir.
This sign flips here.
Yeah.
This
Yes, sir. Yes, sir.
less than becomes greater than. So what is VCM? What is the minimum value of VCM? VCM should be greater than
V,
VB1 minus mod of VTHB,
modulus.
isn't it?
Yes, sir.
So this is the minimum value of VCM, isn't it? So VCM min is how much? VB1 minus mod of VTHB.
P.
Correct?
Yes, sir.
Right. Now tell me, what happens if, what is the max? So we have found out the minimum value, isn't it? Now for maximum value, what? Now tell me what happens if VCM starts to go up. Okay, so this figure is very messy. So draw it again. We have this resistor M0. Okay, after that we have this transistor. This transistor here. Okay.
Yes, sir. This time VGS, this time that gate to source voltage will vary, sir.
Yeah, let's see what
Maximum.
happens. We have this here. This is M3. This is M4. This is M1. This is M2. This is PCM. This is also PCM. This is M0. This is M1. Right. And as again same as earlier, this is I naught by 2. This is also I naught by 2. Cool. So tell me now, what happens if V6 starts to go up?
Yeah, that gate to source voltage will be vary, sir.
This gate to source voltage will.
Yeah, it will increase, sir. The gate voltage will increase from VCM.
So why should it increase again? I mean,
Source voltage just increases, Vx
Only source
increases.
voltage increases, isn't it?
Difference become constant.
Difference has to be constant. Correct. Difference cannot change, isn't it? Current is not changing. Mind it. If the current is not changing,
Yeah.
then the current is not changing through this M3 and M4. The current cannot change through M1 and M2, right? So that
Yes,
is
sir.
why,
Yes, sir. Correct.
if the current is not changing through M1 and M2, the overdrive here, this difference has to remain constant, isn't it? So Vx also increases, right? Now tell me, if Vx increases, which transistor will start facing problems?
M0.
Correct. You see here, M0, the gate is fixed here. M0 gate is fixed, okay? Source is fixed. Now its drain here, Vx, it starts to go up, right? So gate to source voltage for M0 is fixed, but its drain to source voltage, it starts decreasing, isn't it? Sorry, source to drain voltage, it starts to decrease, isn't it? If Vx goes up, then this VDD minus Vx, it starts reducing, isn't it? If Vx increases, right now.
Yes,
So
sir.
M0 can go into linear region, right? So what is the constraint for M0 to remain away from linear region? For M0 to remain in saturation, it's V, it's again, it's VSD, VSD should, or VS minus VD, right? It should be greater than VS minus VG minus mod of VTH P, right? Right?
Yes, sir. Yes, sir.
Correct. So now,
Yes, yes.
so that is why. What is the source voltage here? Again, this and this will simply cut each other, right? This will get eliminated. So we have again VD should be greater than or should be less than VG plus
Reaching
VTH
the
P, right? Mod.
modulation. Yes.
Correct. So what is VD here? What is VD here? VX,
Vx.
right? Should be equal to, should be less than VG is what? Some VB plus mod of VTH P, right? And what is VX here? We have already calculated Vx, isn't it? Due to change in VCM. What is Vx here?
I not
Voltage, right?
VP. Yes. VCM. Yes.
So
Plus of
Vx
KH.
is what? Root over I naught divided by mu p C ox
UMC.
over L plus V Cm plus mod of VTHP should be less than VB plus mod of VTHP, right? Right now,
Yes, sir.
Yes.
this and this go
What is
away.
it?
So now what is the constraint that we have? VCM should be less than equal to
VB minus I naught by
VB minus root over I naught
I naught
divided by mu p C ox
C works
W
W.
over L. Correct?
Yes, sir.
So this is the maximum value, right? VCM can never, VCM should never go above this. Otherwise, M0 will go out of saturation. Right now,
Yeah.
VCM
Yes, sir.
max is equal to VB minus root over I naught divided by mu p C ox
VP C works.
W over L. Right? And this was the minimum value, VCM min. So what is the input common mode range?
Yeah, it should be in the range of VC
So VCM
min to
should be less than, should be greater than equal to what? Should be greater than equal to
uh,
this VB1 minus
VC min, sir.
VTHP.
Mm.
VB1 minus mod of VTHP
Less than
should be less
VB
than
minus
VB minus
VB naught I naught
I
by
naught
square root
divided
of I
by
naught.
mu
VP
p
works.
C ox W over L. Right?
Yes, sir. Exactly.
Cool. Now
Yes,
tell
sir.
me what happens to the output common mode range. What will be the output common mode range? I mean, how much it can go? This V out, how high and how low it can go? Can you calculate it?
Yes.
Again, the same thing. You have to do exactly the same thing. You have to start seeing. So if it goes up, okay. So let's do this. What will happen if it goes up? Which transistor will start facing problems? V out if it goes up.
M2. M2, sir.
Huh?
M2 will affect
Correct. M2 will
linearity.
be affected, right? Because this
It
Vx,
goes to linearity.
Vx. What will happen to Vx, by the way? Tell me. If V out goes up, what happens to Vx? Does it
Uh,
change?
no,
No,
sir.
sir, it will remain same.
It's
Right.
remains.
Because VCM is fixed here and current is same here, so Vx cannot change, right? So if V out goes up, then basically the drain of this M2 is going up, right? But its gate is at the same place. So its drain to source, its source to drain voltage is decreasing for M2, isn't it?
Yes, sir.
Right? So M2 can go out of saturation. Fine. So from that you can find out the constraint on V out. What is the maximum voltage? Now what will happen if V out decreases? Which transistor can go out of saturation?
M4.
Correct. Again the same reason. M4 gate is fixed, source is fixed, but drain is reducing. That is why drain to source voltage is reducing. So M4 can go out of saturation. So in this way you can find out what is the range that you can go to. Okay.
For output also. Yes, sir.
Yeah. Fine. So I guess we should leave it at that today for today. Is there anything else?
Yes, sir. Any more problems are there, sir?
I will
In
be.
the next.
I have other problems here, but that I want you to
Yes, sir.
side out yourself. Okay. I have discussed some problems. Now other problems I want you to attempt yourself. Okay.
Yes, sir. Thank you, sir.
Yeah.
Yeah.
So if there's nothing else, then maybe we can leave for today. Okay.
Sir, in assignments, the capacitor is included, sir. Then how the approach?
Same thing, na. Same old. So this is a sample problem. Okay. So assume that instead of with this you also have capacitor here. Okay. And resistor here. Okay. So tell me
Yes.
what changes because of this capacitor and resistor? Nothing. I mean this simply adds a pole and a zero here. This capacitor only adds a pole and a zero. Nothing else. For common mode range calculations, this capacitor doesn't matter, right? Because capacitor is open
Yeah.
circuited at DC, isn't it?
Yes, sir.
So for common mode calculations, you do not need to worry about capacitor. Capacitor only adds a pole and a zero. That may come somewhere else. Fine.
Yes, sir. Thank you, sir.
Fine. So let's call it a day for today. We'll meet again next Sunday. So thank you for joining. Any doubt can be discussed next week. Okay. Thank you, sir.
Okay, thank you, sir.
Yes. Thank you, sir.